thank you, everyone. Today we are going to have lots of fun because all my classes are fun. And by the way, you aren't just going to sit there. It's very interactive, so I'm going to have quite the conversation with you. And today we're going to talk about the thermal envelope as it compares to the 2018 IECC on the commercial side of things. All right, so this is me in a nutshell. It was basically presented to you. Here's all the information. If you have any questions whatsoever about who I am, feel free to reach out. But I think we should just go ahead and get started. So, since we're going to talk about commercial, my question for you is, when is a building considered to be commercial as opposed to residential? Anybody brave who wants to throw it out there in the first couple of minutes? Kevin. Let me see if I can. I think I allowed you to talk. If you want to unmute and answer the question, I'm all for it.
Five residences.
It somewhat, yes. So how it is determined to be commercial, because the energy code is incredibly different. Oh, all right. We have a couple. Joseph. Or Jim, either one of you? All right, well, we'll just continue on here. So in the energy code, it is not fully defined as you're going to follow the residential provisions if you build out of the IRC, or you're going to follow the commercial provisions if you build out of the IBC. Whereas it might be fairly similar in other areas, such as you build a multifamily building out of the IBC. For your mechanical items, you're going to go to the IMC, not the mechanical section of the IRC. Well, when it comes to the energy code, we are not completely IBC, IRC focused. What we are focused, and as was alluded to, as Kevin alluded to, is the fact that it does depend on the occupancy. So if you happen to be, as it's defined out of the energy code, and as it states, this is for this code only. It's not pertaining to any of the other codes. But for this code, residential buildings are considered to be the detached 1 and 2 family, multiple single family dwellings, which is our townhouses, and Group R, Group R2, R3s, and R4s that are 3 stories or less in height above grade plane. So what that means is you may be building out of the IBC, but you don't qualify as a commercial project per this code. So you may have to take that IBC built building and take a look at it and utilize the residential provisions that you find within the energy code. Oh, just so you know, this particular presentation is focusing on the commercial aspects, not the residential. There is another one going on that is residential. We are talking about the commercial component, but to understand what commercial is, we have to see what the definition for residential is. Oh, so you use the IBC for mixed use. Now you would, again, use the IBC for mixed use, but we'll get there in just a moment, Monica. You're jumping ahead. So it's very specific as far as how it's defined for residential buildings. If you're going to be a commercial building, as it's defined by the energy code, it basically says any building that's not defined as a residential building is then commercial. So anything outside of those R2s, R3s, and R4s that are 3 stories or less above grade plane, those are going to be considered commercial buildings. Now, my question for you also is, when you look at this and you talk about those R2s, R3s, and R4s, I want you to make sure that you're fully aware of that the podium buildings, which in the IBC, yes, if you create a true podium building, they are considered to be two separate buildings. That's for your fire rated construction and the type of material and all of that fun components. When it comes to the energy code doesn't care if it's a podium building. They look at it as it's one entire building. So even if you have 3 stories above a podium, that's considered to be 4 stories if it's all above grade. So then it is going to be a commercial building. I know sometimes there's questions about, podium buildings and how that fits into the commercial / residential item of it. And I see we have a few questions. Oh, since you started the session, can you leave without ending the session? Oh, yes. Oh, yes, no problem. Sorry, I thought that was for here. So the next side of this, as Monica alluded to, is we have buildings that are not just commercial, they're not just residential, so they're mixed use. So how are you going to address those mixed use concepts? Well, when it comes to a mixed use building, you're going to take the components, the portions that are residential that fall under the residential requirements, meaning that it's an R2, R3, or R4 that's 3 stories or less. Those areas will follow the residential provisions, and the commercial portion of it is going to follow the commercial building. So if you have a mixed use building, there is a very strong potential that you're going to be using the entire book and not one side over the other. Now, keeping in mind that whole mixed use residential versus commercial building is still dealing with those R2s, R3s, and R4s. So if you're a 3-story building, the bottom floor is that commercial, and then the top 2 floors are residential, which we're seeing a lot of these days, then that bottom floor is going to follow the commercial provisions, and the top 2 floors are going to follow the residential provisions. So the bottom will do the first half of the book, top 2 will do the second half of the book. Any questions about which side of the energy code we're going to be looking at today? So there we go. All right. Let's jump on in to all of this. So when people are trying to figure out the energy code and how do we comply with it, there is a process that really needs to be followed in figuring out where you're going to go. And the first thing that really does need to be determined is your energy compliance path. And that's determined before you ever kind of create a design for the building. And the reason for that is because there are going to be some intricacies that you're going to have to determine before you can ever kind of put it to pen and paper. And then that's going to design and figure out how you're going to move through that energy code. So when we talk about the various energy compliance paths, there are 3 options that are available. Within the IECC itself, it allows you to utilize the prescriptive path, which is follow section C402 through C405 and C406 and C408, or you can go with the option of that total building performance, which is you're going to follow, the mandatory requirements that you find in the code, comply with the various sections, and then you have to demonstrate that you have an energy cost, an annual energy cost that's 80% of what the standard reference design building would be. Okay. So with that being said, the third option that you do have that is recognized within the energy code is utilizing ASHRAE 90.1. So just by a raise of hands, if everybody can find that button, is how many of you will utilize the IECC before you utilize ASHRAE 90.1, if it's up to you? One person. Oh, there we go. I'm like, maybe I'm teaching the wrong class today. Okay, wonderful. So how many of you typically utilize the ASHRAE 90.1 as your option for demonstrating compliance? Okay. My guess is chances are those that are utilizing 90.1 as their option is it may not be your decision as the designer that's going that way. Is it because of the mechanical design of the equipment or the mechanical equipment, that design that's really making the decision for you to utilize ASHRAE 90.1, which in the past was if you had a more complex mechanical system, you would look to utilize 90.1 as opposed to what was in the IECC. Now, they're kind of apples and apples that they're so similar that you can use either one when it comes to the mechanical pathway now. So those are your options when it comes to the actual compliance paths. Now, one thing I want you to be fully aware of is the fact that just because you say prescriptive actually entails 3 options within it. So you could do the insulation components R value option, which is probably the pathway that when we start talking about prescriptive, how many of you think of the table that has the R values in it when you say prescriptive? So a few of you. And that's typically what most people do think of. That's the pathway that they think of. And that's what their intent is when you're talking about prescriptive and going that way. But there's 2 other options within that prescriptive path. One, the next option that you have is that assembly U factor, C factor, F factor based method in there. And that's where you're taking that assembly approach. And the assembly approach is, where you start calculating and adding everything up to get to those particular values. And then the last option within the prescriptive umbrella is the ComCheck. It's the component performance alternative. So, trivia question. The ComCheck was not always permitted by code. It was not an option within the code. It just recently made its way into the code. So anybody know what edition of the code it made its appearance in? The first one? You can type it in there. So ComCheck became a viable option, an energy codebook recognized option within the prescriptive path in the 2015 edition of the IECC. So with that, oops, there we go. So you're going to see a lot of these little notes, I guess you could say, as we move forward here, because I really feel like I want your projects to be welcomed and looked forward to by all plans examiners. And so some of the things that I'm going to provide you are little tidbits that I hope you take as, I'm going to take that and I think that's a good idea. I'm going to make it easier for the plans examiner to find this information so we can move on. And so, and I've talked to the emerging leaders out of, with AIA here in Colorado and talked to them about this. I've talked to lots of architects all over the country about this, quite honestly, is you use this code analysis to provide a lot of information for the code official, the plans examiner, to let them know this is how we designed the building, right? You tell me that it's going to be a 2B construction. I'm like, okay, you're going to tell me what occupancy, you're going to tell me what your fixture schedule is. You have a whole bunch of items that you put in there, basically kind of setting the stage for this project and what you did and how you designed it. So I think we truly are at the point where we need to be utilizing our code analysis and incorporating some of the energy components in there. And I think that will help you in getting your projects submitted and through the whole plan review process. So I suggest listing your compliance path within your code analysis. And if you do choose to go prescriptive, say which one of those three options you would like to utilize or that you had designed with this particular project. All right. Now that we've kind of figured out, all the lovely compliance paths, we're going to take a look at the rest of this as if we're using the R value-based option. The next thing is, because we are going prescriptive, it is required that you must have and incorporate an additional efficiency package option, which is what C406 tells us. So when you're designing things, this is one of those items that you also have to incorporate into your design. Now, sometimes those options are not necessarily architectural type of options. It might be mechanical, it might be interior lighting, power densities, but all of those kind of revolve around that thermal envelope. So if it isn't a very strong thermal envelope, they may not be able to use higher efficient equipment because the size of equipment that will be required can't meet those particular items. So okay, so we have a question. Can you help us understand why the building departments in Northern Nevada require multifamily housing projects, commercial IBC, be completed using ResCheck and not ComCheck? It's going to depend. If they're 3 stories or less, they would be required to utilize ResCheck and not ComCheck. I'm not sure if they are higher, larger storied buildings. That might be, if they're 3 stories or less, they absolutely go ResCheck and not ComCheck. But I'm not sure. They may have some sort of amendment maybe to or a policy that's in place. Does that answer your question, Jim? Yeah, no problem. I'm glad you're asking questions. I will tell you, I love questions. I love asking them. I love people asking them of me because I really feel like that's how we learn. So now, the other thing I want you to keep in mind as we're talking about these additional efficiency packages is the fact that it is only a requirement when we are doing the prescriptive path. Now, some people say, why are we doing this for the prescriptive and not the total building performance option? Now, if you remember, for the total building performance option, they have to demonstrate that their proposed design is 85%, the cost of their energy cost is 85% less than what the standard reference design annual energy cost is. So to make sure that we have, compliance paths that are as equal as they can be as far as, energy efficiency and so forth, that's why this was created. You have the additional efficiency package and you have options in how you're going to be able to meet that. So it's not just a prescriptive compliance path option in the sense that they both kind of do it. One is just taking little bits everywhere and getting it down that 15%. So let's go ahead and see what these options are. So you have 8 options. You can have more efficient HVAC equipment, which isn't always going to be the case because not all HVAC equipment can have a higher efficiency than what is federally there. The federal efficiency rate might be 80%, and the best you can get is 82, and that's not going to be 10% better as that's required. So that's something to keep in mind. Reduced lighting power is probably one of the most popular ones that I see. Another one is your enhanced digital lighting controls. That one's starting to get a lot of weight to it because I think for a while there were some concerns about lighting controls. On-site renewable energy, dedicated outdoor air system, or that DOAS system. You can have reduced energy use and service water heating, enhanced envelope performance, and reduced air infiltration. Now, what I would say is probably the one that to be mindful of is if the one that you choose is the reduced air infiltration, you need to make sure that it's very, very clear and explicit for everybody who's going to touch that project, because it's going to be those one, that one time, that one penetration going through the wall that didn't get attention paid to, that's going to end up causing the project to not meet this requirement. So the one thing that I brought all of these in here, and the reason I brought all of these in here, because like I mentioned, all of these are affected by your thermal envelope. The thermal envelope really is going to make or break how things will work. You might have higher equipment, the lighting, so forth, but probably the most architect focused is that enhanced envelope performance and the air infiltration rate. And the enhanced envelope performance is that 15% better than code, and you would utilize the component performance alternative for that. Oh, here we go. So how does COVID air quality needs come into play with these options? I think that's a great question when we start talking about the air quality, right? Because I think there's a lot of concern about building tight and then ventilating right. And when we start talking, like residentially, I think there's been a lot of focus and a lot of really good practices out there, on best practices that are out there that are getting utilized, and these projects are able to meet the air leakage rates, right? So that they're not leaky houses. Where I think there is, we'll just say, definitely room for improvement is on the commercial side. There hasn't been a lot of attention paid to that. So I think once the attention is really paid for it, the second part, just like on the residential side, is dealing with that ventilation system. Now, the ventilation and the mechanical provisions that you find not only in the energy code, but also within the IMC really does take that into account and make sure that we have the correct amount of ventilation. When we look at the residential side, right, you have your whole house mechanical ventilation. You can do exhaust, supply only, or a combination thereof, and you have a number that you're going to meet, right? When we look at the requirements on the commercial side, there's a whole table that you have to do and all the calculations that are involved with all of that. And the energy is also a part of that when you start looking at 403 and the provisions that are in there. Some of that could pertain to things like, your DOAS system, or your, air economizer that may be getting utilized. And then, like I said, the air leakage rate. The air leakage rate, this is going to be an incredibly difficult one, in my opinion, right now, with the common practices to be met. It's not impossible, and I think it's really doable. It's just making it very clear what the intent and what the design is going to be. Whoop. There we go. So again, our code analysis, I think it would be great, and a great way of conveying that information. So it's just right there. And then the plans examiners and anybody who touches the project after that knows. List your additional efficiency package option in your code analysis if you're going prescriptive. Then it makes it very clear. Everybody knows what they have to pay attention to. All right. So now that we've had lots of fun and having those lovely, conversations about, the additional efficiency package and which compliance path we're going to utilize, let's start thinking about that actual design of whatever building that you're going to do. And probably before anything is said and done and you determine any R value to go anywhere, you really have to look at and determine and figure out where your thermal envelope is. Now, in section C 103.2.1 does tell us that a building thermal envelope has to be depicted onto the construction documents. So if I look at this particular, section here, what I always say is I should be able to trace the thermal envelope without lifting my finger, meaning that there's a break in the thermal envelope and that it continues all throughout the building. Now, the thermal envelope is there really to be that barrier between what's conditioned and unconditioned. We want to make sure that whatever space is, however it's being treated, if it's being conditioned, we're making sure that whatever that conditioning is breaking the second law of thermodynamics and it's staying where we want it to be, right? And to do that, we have to know where we have to pay attention for that thermal envelope to be. And so this is the result of that. It came into the code, I think in the 12, maybe it was the 15, saying that you have to depict it on the plans because there are areas that are in question. There's probably more areas that come into question, maybe on the residential side of things, right? Garages, attics, crawl spaces. And while attics and crawl spaces could be in question here, there are some areas too that come into question. Is that storage unit, maybe on the exterior side of the building, is that inside the thermal envelope, outside the thermal envelope? Is that mechanical room inside the thermal envelope or outside the thermal envelope? And is that mechanical room required to be, thermally isolated because outside combustion air is being dumped into the room? And so we need to make sure that we're not bringing in that unconditioned air into a conditioned space. So there's a lot of things that having that thermal envelope depiction really does help in trying to get that along there. Now, as you can see on this screen, just because it shows insulation, it does not necessarily mean that it's there because it's a, part of that thermal envelope. I don't think when we look at this roof area is, I'm sure this exterior wall is, this floor here and this floor here come into question, floor double Fs, they come into question. Then we've got this nice little drop down here. There's a whole lot here that for me came into question when I looked at it. So just because you're showing insulation on the section there doesn't always mean that it's there because it's there for thermal resistance. Why else would we have insulation shown in an assembly? Anybody think why we might have? Sound. Excellent, Kevin. You're absolutely right. We got sound. Insulation is going to be in those locations for sound. So if this floor is being insulated for sound, a great tool would be is to say, okay, and I've seen this done all the time now, is where they just make a note within the floor that says sound. Then I, as a plans examiner, know that that insulation is there for sound. What else? Smoke or fire control. Excellent, Larry. Absolutely. We know that this is a group R occupancy. We know that in this multifamily unit that we are going to have that horizontal fire separation. So that is exactly probably what's going on here. And it was, but I mean, that's another one. Why else might you have insulation in an assembly? All right. Well, another reason why you might have it is you're looking at the thermal envelope components, right? We're trying to resist the thermal, the heat going in or the heat going out. The other component that you also have to keep in mind is your vapor retarder assembly. That can include insulation as part of it, whether it happens to be it's craft-faced batt insulation, or you're going to do the option that's going to get you to a class 3 vapor retarder, so you have that continuous insulation on the exterior. Whatever it is, that insulation can also be part of a vapor retarder assembly. And so that we have to keep it in mind too, as we start working and thinking and working forward with all of the fun and excitement that the Energy Code has to offer. So here is the table that, we all kind of look at and think of. It's very comparable as to what you would see if you were using the U factor, C factor, F factor table. It's broken out by climate zones. And then underneath the climate zones, it's subdivided. And it's subdivided so that one column is all other and one column is group R. Now, what do you notice about the differences between the column of all other and the column of group R? Anyone? Well, if you notice, the numbers or the requirements, the values that you see in the group R column are higher than what you find in the all other columns. Because if you think about it, group R entails what? Places we live at, wherever we're residing, whether it's kind of on a permanent nature or temporary, as even in a hotel, right? The idea is we want to make sure that you're comfortable wherever you're going to live. But we don't care if you're comfortable where you work. I always do that, because that's otherwise, why would we have the differences? Let's just go with the higher one and go with it and not even have to worry about it. But it is broken up in that fashion. So you'll notice that the group R values will be and usually are a little bit higher than what you'll find for the all other options. Oops, there we go. So let's talk about, what we see within the table here. And one of the items that are in this table is that CI. And that CI is indicating that it's meant to be continuous insulation. So for continuous insulation for the Energy Code, it's talking about that it has to be continuous and across all the members, that it can't be interrupted by anything. And basically what they're saying is you can't have any framing members that are going to interrupt that insulation. Otherwise, at that point, it's considered to be cavity insulation and not that continuous insulation. So let's talk about the different types of insulation there are. Now, as you see on the screen, these are probably the most utilized insulations that we see out there in the field right now, right? We've got batt insulation, fiberglass blown in, cellulose blown in, closed cell, open cell, extruded polystyrene, polyiso, and the expanded polystyrene, right? I don't know about you. Has anybody had lots of fun with the expanded polystyrene insulation or are familiar with what it is? Yeah, all the little styrofoam balls kind of glued together type of deal. But if you cut them, they all come flying off and make a lovely mess everywhere. But that's what that extruded or expanded polystyrene is. So the difference between the expanded polystyrene and the extruded polystyrene is the formula for the expanded is, right, it expands to these like little balls type of deal. When it's the extruded polystyrene, what, like I always try to explain it is, I don't know how old everybody is, but I'm thinking back to my day where we had the Play-Doh factory and we had that big old cone and you stuff the Play-Doh in it and you crank the little shaft there and it extruded these designs out on the other end. So that's kind of what the extruded polystyrene is. So as you can see, this the various types of materials really can have a huge impact, because you could say, hey, I want to use spray foam in the cavity. 2x4 cavity, if you're using open cell spray foam, you're not going to get an R20 in the wall. But if you use closed cell spray foam at that point, then you are going to be able to get it in the wall. The same can be said when you start looking at the fiberglass bat insulation, knowing how much room you need and whether that bat insulation is going to do it. Because say you're going to put in an R30 in the wall. Well, an R30 bat insulation isn't going to fit in a 2x4 wall or a 2x6 wall or even a 2x8 wall. The amount of space that it would need would be a 2x10 wall or what have you. So the different R values really do make a difference in your design. And I threw this in here just to kind of show all the this is for the bat insulation and the amount of space, depth in a cavity that bat insulation needs to meet the R value when you're trying to get that in there. So just FYI, a little bit of information for you. I like to give information. Whoop. Okay, so now we're just going to walk through that table that we looked at and talk about some of the components that we find in the energy code for it. So the first is dealing with the roofs and the insulation entirely above deck. So when we're doing the insulation entirely above deck, you're going to comply with C402.1.3 or you're going to comply with C402.1.4, depending on which option you use. And you're going to have that continuous insulation that's required in there. Now, how many of you knew that if you utilize continuous insulation entirely above the roof deck on the 2018, it is required to be installed in a minimum of 2 layers? All right. Whew. I was worried there. We got a few. Now you all can say, hey, next time somebody asks me that question, I know we need 2 layers. So not only do you have to have the 2 layers, then you also have to have the joints and seams staggered, which, oh, well, good. I'm glad you know that now. It's so important to know that those joints and seams need to be staggered, because I'll tell you, I've gone out where it's on here, it's showing the 2 layers like what you see on the screen right here. But the one thing it didn't do was say anything about the staggering, and what they did is they had 1 layer here that ended here, so they just placed the same layer on top. What did you create in this space? You created a perfect pathway for that water, if it gets through there, to be able to make it there. Staggering the joints and seams allows that if the water were to get here, down the one, little joint there, it's going to have to travel to get to another spot that can actually get down into that roof, the sheathing for that roof. So it's kind of a, we're trying to help out the resiliency and the longevity. And then you say, Hope, we don't have a lot of water. And I say, I understand, I'm in the same place with not a lot of water, but if there was a possibility for water to get there, we want to make sure it doesn't get trapped in there. How does the degraded value of polyiso over time affect its use? That is a very good question. And what I can tell you is, obviously the idea is that the insulation is going to be able to last for the lifetime of the building. Now, part of that is going to deal with the installation of the material and how it's utilized within an assembly, how long that longevity is actually going to be. As far as the degrading value of the polyiso, I would not be able to give you very specific answers to that, but you do have my contact information. And what I would say is send me an email, because I do have a colleague who works in the rigid insulation industry. And in fact, I'm speaking for them next week. And I'll see what we can do about getting a very specific answer for you, Gary. Now, the other thing that you have to keep in mind when we start talking about those roof assemblies is that, there's going to be times that you're going to have those varying thickness, because we have to realize that we definitely want to taper that rigid insulation. Why do we want to taper the rigid insulation, you ask? And I say, that's an excellent question. The reason we want to taper it is because we typically have roof drains, scuppers in locations, right? So we want to make sure that we have those roof drains. The water, in theory, when we have water, is draining into those drains and not staying stagnant on the top of the roof. So there is going to be some tapering involved with this. And it does say if it's tapered, it's very less than an inch in it, there's still kind of be considered with it. But when you have various thickness all throughout, because maybe you're dealing with a curb or whatever the case may be, equipment requirements, then you have to start averaging out whether you're actually getting that, R25, R30 continuous insulation throughout. So keep that in mind when we start looking at this. So I want to show you this image on the screen. And I just gave you the answer somehow. If we look at this particular design, what do we have that's good and what do we have that's bad? Anybody see what the issue is with this particular image? So the issue with this image is the fact that it does not provide us what the R value of the insulation is. It tells us 3 layers of thermal insulation, each are 2 inches thick, staggered overlaps. There's 2 things that are wrong with this, and I probably should have listed both of them. One is if we go into R103 or C103.2, and there's a list of items that are required to be placed on that construction documents. One is you have to give me what the R value of the insulation is. The second one is you have to tell me what the material of the insulation is. The reason why we want to know the material is because, one, if we recall, we look back here, right? We've got all these various items that we have to address. One of the items that we have to address is that fire-resistant rated construction. That type of insulation may be dictated as to what is listed in the assembly. So that material may not be permitted by the particular assembly. The other thing is the vapor retarder assembly, as somebody, Randall, was referring to a little bit there. So with that, those are there we go. That's what's missing here. We need that R value. I need to know what type of insulation that is going to be there. I thought staggering the joints was intended to help prevent moisture vapor from the inside, making it to the membrane and condensating on the underside of the membrane in cold climates. That is probably part of it too. But think about if the water does make its way in. If you make its way in and you have 2 joints right here that are one right after the other, then it's got a clear path to get there. There's more than one reason in all of those things, but that is an excellent point. So what do you guys think about this particular image on the screen? The one on the right. So in this image, it tells us roof membrane on 5 inches of rigid insulation. Again, it doesn't give us what that R value is. This one says rigid insulation. Now, if we look at the roof, they did put this nice little values table and said, hey, the roof is going to be an R25 continuous. So 5 inches would tell me that it's probably an R5. But and then it just says rigid insulation. Rigid insulation could be the extruded polystyrene. It could be the polyiso. And needs 2 layers. Yes, very good. That is definitely a problem with this one. Fortunately or unfortunately, it depends on how you look at it. This was submitted to an older code. The older code did not require that it have the 2 layers. The 2 layers came in, I think, in the 18. Oh yeah, see? Good job, Anonymous. All right. Now that we have had a lot of fun with our above deck roof insulation, now let's talk about metal buildings. Metal buildings are required to have their roofs. They have to have an R19 plus an R11 LS. That is what's required by code. And then there's this nice little footnote B. If we look at footnote B, it says, hey, if you're going to utilize the R value option, it also has to include a thermal spacer in this particular design. Otherwise, you have to go and use the U factor compliance method. And it doesn't mean that you are just using that U factor method for the roof. You then have to use it for all of the components of the metal building, which, good, bad, or ugly, you may or may not want to do all of the fun and excitement that is involved with it, which includes you have to provide, you know, the, I don't know why it keeps jumping backwards, that you have to comply with the, sorry, I lost my train of thought, with providing the documentation as to where you got all of those values. So here's an example on a set of plans for a metal building where they utilize that thermal break right there. Now, keep in mind that a metal building is not a building that's using metal studs. Now, a metal building is not defined in the IBC. It's not defined in the IECC. But if you go into ASHRAE 90.1, it does have a definition of what a metal building is. And basically, all of the components, the base components of it, are made of metal. You've got girders and purlins, and then it has that metal skin to it. Now, you can add additional exterior cladding to that, but it's a metal skin to it. And I think we've probably all seen the, you know, PEMBs, pre-engineered metal buildings. That's the type of buildings that this requirement would be required to comply with. Now, when we look at that, the LS says a linear system. So that linear system has to contain where it has that vapor retarder on the bottom there. And it's installed below the purlins. You know, you look up because it can't be interrupted by any of the framing members. It's you know, that continuous concept. And then an uncompressed, unfaced insulation is going to be resting on top of that membrane. And that's usually where you have the concept of you got insulation going in between the purlins, and then you have another layer of insulation that's going, you know, above the purlins and that thermal break right there. So a lot of times what I see called out for metal buildings might be something of what you see on the left-hand side here, because what we see on the left-hand side here is we've got, and it doesn't, I cut it off, but it has insulation here. It's got a thermal break. It's got more insulation up here, and we've got our roof deck. So this option on the left-hand side can still use the R value option because it has that thermal break. Now, the one that you see on the right-hand side would not be able to use the R value option because it doesn't have that thermal break requirement included in this. Now, what it does call out is this simple saver system, which is probably 9 times out of 10 is what I get when we talk about metal buildings. They're like, I'm going to install the simple saver system for the roof, and then they have it for the wall too. They don't have to, they just have to comply with the, you know, all of the requirements for it. It's just a simple, easy one. But something to keep in mind is when they say that simple saver system, not all of the simple saver systems, if we look at right here on the left-hand side, have that thermal block in it. You can get a simple saver system that doesn't contain the thermal block, which is what they had on this right-hand side. If that's the case, then we have to go to the prescriptive U factor option and look at that. And then that has to translate to all of the components of that particular building. All right, so attics and roofs, I think we're probably very, very familiar with attics and roofs. I think probably the biggest thing is just understanding that when you place insulation on, you know, those suspended ceiling tiles, and typically that happens because you've got an office right next to a restroom, and whoever's stuck in that office does not want to know the business of whoever is in the restroom, right? So the insulation is there. It's typically for like that sound attenuation, and that's perfectly fine. It just can't count and be part of that thermal envelope. At that point, that insulation, if it's part of the thermal envelope, would need to be located in the attic space, whether it's, you know, at the ceiling level, because you've got a vented attic, or at the underside of the roof sheathing if it's an unvented attic, just depending on how that works. But what I like about this one is, if you notice, it gives us both the R value of the insulation, and it also gives us the insulation material. So here's our above grade walls requirements. And again, you know, you do have to comply with the particular table. It does have information as far as what would be considered as a mass wall. Now, with mass walls, how many of you design buildings and you're utilizing a lot of mass walls with them? Okay, so we have a few. Wonderful. So when we start talking about those mass walls, you'll notice that they're required to have that continuous insulation. Well, for them to be considered as a mass wall, there are some very specific requirements. So you would have to go and take a look and see. And in that particular section, it tells us that it needs to have a weight of 35 pounds per square foot of that wall surface area, or it has 25 pounds of per square foot of the surface wall area where the material is not more than 100 PCF. Or the other option is you start looking at the heat capacity. So if that heat capacity exceeds the 7 BTUs per square foot option, then it would be considered a mass wall. Or if it exceeds 5 BTUs and the material weight is not more than 120 PCF, then those are all considered to be mass walls, and you can do the continuous insulation. Now, anybody utilizing the insulated concrete forms for their mass walls? I call them adult Legos. All right. I think the adult Legos are a lot of fun. So in that instance, you're going to be looking at the mass wall requirement, the above grade mass wall requirement for those. Metal buildings, all metal buildings are going to have a cavity insulation plus a continuous insulation requirement. It doesn't matter which climate zone that you're in. But when we start talking about the metal or wood framed walls, you'll notice that a couple of the climate zones do permit just having that R20 cavity concept to it. Until you get into climate zone 5 in the group R occupancy, then there's no cavity only option. You will have to also do continuous insulation. So below grade walls, let me just ask this. Do you typically have a lot of designs where you're utilizing for your commercial buildings a basement or a below grade wall design? So we have a few. Okay. Well, for those below grade walls, if you happen to be in climate zone 3, you actually have no required to do anything with those walls when it comes to the thermal envelope. You can declare them as part of your thermal envelope, but it's not required that any certain amount of insulation is in there. Now, once you get into climate zone 4, then it's all continuous insulation that is required. Now, when we talk about the installation of that continuous insulation, you are going to go from the top and of that wall and extend it down 10 feet or to the lowest floor, however it's going to be. Sometimes you have those really tall walls, and if it's a really tall wall, you're only required to go down 10 feet. Probably is easier to go through the whole way, but you only technically have to go the 10 feet. To classify as a below grade wall, and this is where it's incredibly important to understand, is 85% of that wall has to be below grade for it to be considered as a below grade wall. Any questions about that concept? All right. Floors. So we know that floors are required to, their mass walls, or mass floors are required to be continuous. If it's a joist or framing, you've got a cavity only. It's always said that when we talk about that the insulation is required to be in constant contact with the underside of the floor. Now, there is an exception to that. And one of the exception is the insulation applied to the underside of the concrete floor. So we got those mass floors is permitted to have an airspace, but you're only allowed an airspace that's a maximum of 1 inch to it. Now, the other thing, and for some reason it is not on here, and I don't know why it's not on here. But one of the things also is it does talk about the, oh, I have some hands up. Are these leftover hands from before? Or you have a very specific question? Okay. So one of the other things to kind of keep in mind is when we're designing those mass wall floors, is anybody thinking about how you're going to maintain that thermal envelope, or are you doing everything within your power to have it so that you don't have to incorporate the or have to include those mass floors as part of your thermal envelope? There's no right or wrong answer, just question on it. Because I know that's one of the questions that really comes into play. And a lot of times that I get that question is when we start talking about those podium buildings, right? Because there's questions about, you know, how am I doing this? Because we've got, you know, per the IBC, we've got one building on top of another building, but how the energy code looks at it is it's just one building, right? That's only to deal with your fire assemblies, as far as, you know, why you have the two buildings as you do. So, the thing that I wanted to kind of bring up is, you do have some options. Obviously, you know, you're trying to separate things, but it may be something that I have seen where they fur it out a little bit and they rest it on the furred out design of it. It kind of goes against having the podium build for the two. But it is something that I think a lot of people are concerned with and trying to figure out too. Now, in this, it is just showing one exception in there, but there is a second exception to this. And this is dealing with those framed floors or those joist floors. Instead of having it in constant contact with the underside, it says you're permitted to have it rest on top of the sheathing or the continuous insulation that's located on the bottom of the floor joist, right? You're permitted to have it rest here as long as what you do is, if your exterior wall comes here and your subfloor is right here, you have to continue that continuous insulation all the way down so there isn't a break in the thermal envelope. So you'd be carrying that continuous or that exterior wall insulation basically into that floor cavity, and then carrying the floor cavity or the floor insulation through that. So here's something that I have seen. You know, they're putting a bat insulation now. This was not dealing with that podium concept. I think the podium concept is probably the biggest one. But the other option here is, as I'm explaining here, you see, here's our floor insulation. It's resting on top of the rigid insulation, and we carry down the insulation for the exterior walls down into the floor cavity. So that's what that particular exception does allow for us to do. And let's talk about slab on grade insulation. Slab on grade, if you are climate zone 3 and you are not heating your slab, you can go to sleep right now. But if you're designing and doing it anywhere outside of climate zone 3, you're going to want to pay attention. So how it works is if you have a slab that's less than 24 inches below grade, then you will be required to install slab edge insulation. Now that slab edge insulation can be either on the interior, the exterior. I've seen a combination of the two, and I'm not too worried about that. But the most important thing is it must start at the top of the slab and extend down. Now you have options as to how you want to do it. And if we look right here, if we place it on the exterior, it starts at the top of the slab, extends down. And the wonderful thing on the commercial side is it has to go the distance or to the top of the footing. So it says for 24 inches, if you have a foundation and it's 18 inches and you start from the top of slab and you go down to the top of the footing and that's 18 inches, on the commercial side, you're good to go. So you can also do that on the interior side of the foundation wall. Now, I have heard a lot of questions about the viability of being able to do that. How much heat is lost at the bottom of the slab edge? You mean the slab edge down here or the slab edge here? Oh, you're talking about the slab edge, not the bottom of the insulation. Let me put it to you this way. Currently within, if we were looking at this on the residential side, there is enough concern about it that residentially, if you qualify and you are required to have slab edge insulation, you are not permitted to trade it off. It is a non-tradable option within the code. Now, on the commercial side, it is set up a little bit differently, that it has not been deemed that you cannot trade it off. There is a lot involved with it. So that slab edge insulation does a whole lot. It's not only there dealing with that heat loss, which it will, it helps with that heat loss. But if you think about, let's say you're in the, you know, wonderful patio, enjoying the beautiful outdoors, and you get a cup of a mojito, right? They bring you your glass of mojito or whatever. And what's all over the outside of it? Condensation. Because the inside of the glass is colder than the outside, which is obviously warmer, and it's causing that condensation. Part of the slab edge insulation is there to help with the condensation concept too. It's a multiple type of concept. I can't give you like specific numbers, but as I mentioned, it does have an impact for it. You can do the option of going from top of slab, bottom of slab, and extend it for the rest of the distance under the slab. Oh, getting back to this one that's fully on the interior side of the foundation. I know a lot of times there's concern about that because it's going to be dependent, and it would really determine your design by having the conversation with the structural engineer. A lot of times the structural engineer is calling out for a control joint to happen at that particular junction. So there have been structural engineers that say absolutely you can use that slab edge insulation in the capacity as a control joint. That's not all the time and in every situation. So it would be a case by case basis. So you're probably looking at more of a exterior type of design for the slab edge insulation. But you can also do this far one on the right here, where you start at the top of the slab, continue down the slab, and then extend away from the foundation. If you do that to meet the distance requirements, if you do that particular option, you will be required to have it covered at least by 10 inches of dirt or pavement, concrete, something along those lines. Now, if you do have a heated slab, at that point, it is required that you insulate the entirety underneath the slab, and it's a minimum of an R5. Now, that's the requirement no matter what. Then you will have to also have slab edge insulation, but the slab edge insulation only has to go to extend to the bottom of the slab. So it doesn't have to go, you know, below the slab. So if that slab is, 22 inches, you only have to go to that 22 inches. You don't have to extend it below that. Oh, it keeps going backwards. So here's an example. I'm seeing this probably more often now, where I'm getting this particular design where part of the insulation is going at the exterior side, and then there's some that's going on the interior side of the design because of, sometimes you need the tension that slab has for that foundation. So there isn't necessarily a control joint going on right there that would allow for that much insulation. So then it's kind of like a ledge. It's a ledge that's going on there, not only for that insulation, but also for that exterior cladding that's going on. And then we see the insulation on the interior side below the slab. And then because this was a heated slab, it did put the insulation entirely under that slab too. Now, what I typically will see, and let's get some, if it's going to let me draw. Nope, it's not going to let me draw. Okay, so a lot of times I'll see a detail where there's no insulation on the exterior and they start the insulation from the bottom of the slab and extend down. That isn't a design that works because all the designs have to start at the top of slab and extend down. Otherwise, in that particular design that I just mentioned, you are adding material to a project that's doing absolutely nothing. So then you're wasting money on it because it isn't going to fulfill the intent of it. So skylights. I think I probably hear a lot about skylights, and skylights are required. Anytime you have a space of 2,500 square feet or more, and 75% of that roof area has a height of 15 feet, then you are going to be required to have skylights, and you have to have a minimum of 3, but not exceeding more than 6. Once you get to 3 or more than 3, then you will have to have some lighting controls for it. Now, this requirement also is only pertains if you happen to have below it an office, lobby, atrium, concourse, corridor, storage space, gymnasium, exercise area, convention center. I can't tell you how many convention centers I am in that have no skylights in them. And I'm there, and it's very, very dark, and it's very, very, it's not very happy. But I've been a lot of convention centers that I'll be there for weeks on end, and it's great because they've got the skylights in there. They're wonderful. Automotive service areas. I can't tell you how many times I don't see this in automotive service areas, manufacturing space, non-refrigeration warehouses, retail stores, distribution sorting areas, transportation depots, and workshops. So we have a question for warehouse, airplane hangar type buildings where there are large openings that remain open for long periods of time. Are there exceptions for not doing below grade insulation? Do you mean below grade insulation as in slab edge insulation? Or when you are talking about below grade wall insulation? Slab edge insulation below grade wall. Okay. Okay. So for the slab edge insulation, the only time that there's a real exception for that would be is if you were in climate zone 3. If you're in climate zone 3, it wouldn't necessarily comply. But if that building, that area, the warehouse airplane hangar is not being conditioned, if it's not being conditioned, then you would not have to comply with it. But if it's being conditioned and you are in climate zones 4 or 5, you would be required to have that slab edge insulation or below grade wall insulation, unless you are trading some of that off. Now, as far as the Botanic Garden building where the entire roof is a skylight, that is an excellent question. And where that would come into is if you go into now I have to look real quick. It's C402.1, and I can't remember which one it is. There is an exception for greenhouses as far as having to comply with the skylight requirements for it. It talks about as far as the if you happen to classify as a greenhouse, and that's defined within the energy code, meaning that your sunlit environment, which I would imagine the Botanic Garden building would be, where the entire roof is a skylight, because the idea is you're bringing all that sunshine in because you're growing all of the plants in there. So in that instance, all of the skylight component wouldn't necessarily have to comply with the full provisions of the energy code. Parts of the thermal envelope would not come into play, such as maybe those control requirements for the lighting aspect. The controls for the lighting aspect would be required, but the U factor solar heat gain coefficient of that lighting and the percentages of the skylight requirements wouldn't fall into play for it, because you're following the provisions that 402 has when we talk about those low energy usage and the energy use buildings. And what falls under that is the greenhouses. Now, greenhouses do have to comply with the mechanical and the electrical and the surface water heating requirements. They just don't have to comply with the full extent of the thermal envelope component. I hope that answers both of your questions there. Is there an alternative for clear story windows in lieu of skylights? The skylight section, what it does allow for is the tubular daylighting devices. That is an option that can be utilized in lieu of skylights. The clear story windows are not included in that, because for the skylights, if you go in and you look at the definition for fenestration, it gives you at what degree it's considered to be vertical fenestration and what degree it's considered to be a skylight. I believe it's 60 degrees. So typically those fall under the vertical fenestration as it's defined, and not the skylight defined. So no, it would still have to have that skylight that's falling into the roof assembly design. I hope that answers your question. These are great questions. I'm so glad you guys are asking them. I love it. So here's an example of what we would find on a plans when it comes to this particular gymnasium. Now, we talked about skylights. We got to remember that not only do skylights have to, you have to have them installed in certain instances, they also have to follow certain parameters. One is that you have to insulate it to that roof above roof deck R value, or at least the curb has to be an R5, whichever is less. At this point in time, the R5 is what you're going to need to do because the R5 is probably the lesser of the two options there. So we've talked very briefly through the table and kind of walking through it a little bit. If you have questions, feel free to shout them out in the Q&A. If not, if you think of them later, send them my way. I'm happy to answer them. Sometimes I don't cause questions for you until an hour afterwards as your brain's kind of processed all this information I'm throwing out to you. And I get that, and I'm happy with that. So I'm happy to do it. So the next thing let's look at is those fenestrations, because insulation is not all by itself. It also has the fenestration. So when we look at table C402.4, we have to think about the U factor and the solar heat gain coefficient. And as you can see, it's kind of based on, what, and this I believe is the wrong table that's shown in here. It should be showing the, oh no, I guess not. Yeah, it should be showing the, not fixed and operable, but it should be showing what the, it's directional, whether it's facing north, south, east, or west. I had some problems getting that in here, so apparently the wrong one finally made it in there. But what I really want to talk about is disregard the numbers on there. What I do want to talk about is the solar heat gain coefficient. And the solar heat gain coefficient is dependent on a few things. One, if we don't look at the table and we looked at the correct table, it would show you that it's dependent on which direction it's facing. The other thing is it is dependent also on the projection factor as to what the maximum solar heat gain coefficient really truly is. Now, my question for you is, how many of you know how to determine and decipher the projection factor for windows? How many of you have done it or know how to do it? Okay, so because we don't have everybody's hand up, we're going to walk through this particular part of the requirement out of that particular table. So basically, how we determine that is we're going to take H and divide it by V. So to get the value of H, we are going to measure from the face of the glazing and measure it to the very edge of the overhang. And that's going to give us our H. Then to get V, we're going to take the bottom of the glazing, the fenestration, and we're going to measure from there to the underside of the overhang. And that's going to give us V. So we take H and divide it by V. So this is where, we're going to have the conversation. So we'll see who has the fastest phone right now. If we take an H is 15 and V is 66, what would our projection factor be if we use this calculation? Oh, nobody has their phone. Ah, Kevin, gold star for Kevin. Yes, your projection factor is going to be 0.22. So if we go back, and again, I apologize for having the wrong table in here. If we come back here to look at what the projection factor would be, we would need to be looking at this middle row because it's more than 0.22. But it's less than 0.55. So our requirement would be is our maximum solar heat gain coefficient, dependent on which direction that it's in, would be based off of that middle row. So a lot of times what I find is that that information isn't necessarily placed on the plans. Sometimes I might get a note about it, maybe in the what do I want to say, in the spec book, but it really needs to be placed on the plans. And the reason I say that is because we need to make sure that we're getting the correct U factor and we're getting the correct solar heat gain coefficient as far as how it's being designed. And the reason for that is because the glazing is not just part of the thermal envelope and making sure things are comfortable. It absolutely is, but it's also part of when the design or the mechanical engineers are designing their system, and they have to do their heating and cooling load calculations, which are required by the energy code and required by the mechanical code. They have to incorporate those values into that. And if by chance that information is not very clear, so that those are the windows that are getting installed out in the field, then it can affect whether that mechanical equipment is sized properly for what the actual intent is. Oh, isn't glazing in skylights and elsewhere inherently low R value, approximately R2? Therefore, wouldn't the energy loss through skylights be more than the energy savings due to daylighting? Well, the skylights are typically done by the U factor. So the R value is the resistance to thermal, and that's what the R value is. And typically you get that with the insulation. For glazing, and it's listed as a U factor because that U factor is a value of the heat passing through an assembly. That's why it's a U factor for glazing and R value for the insulation. But when you take into account for the whole assembly, if you use that particular that R value approach or a compliance path approach, that's why it's the U factor, because it's the assembly. How much is that assembly resisting the heat passing through? And that's why you're using that 0.3 U factor as opposed to an R20 in the wall type of deal. And then the C factor, just so you know why it's a U factor, a C factor, an F factor for that particular pathway. The U factor is dealing with the heat, the passage of heat through an assembly, which would be, maybe roof, what have you, the walls. The C factor is dealing with the slab on grade, that slab or the slab when it's a floor. Think of it, the C factor is concrete of the floor. And then the F factor is dealing with like the foundation walls. It's dealing with the vertical concrete and not the horizontal concrete. So F factor is foundation, C factor is the concrete in the floors. So that's how that table is divided up now. So I would say that there are a couple of things. The reason why the U factor is going to be so incredibly important is the fact that the two areas that are very impactful when it comes to heating and cooling loads are your roof and also your fenestration. So when you start talking skylights in a roof, you're kind of hitting a 2-for-1 there too, because you've got the fenestration and the roof that's going to have such a huge impact. Now, I don't have strict numbers as far as the difference of the loss. How much loss do we have with the heat loss do we have with the roof as opposed to the heat loss with the skylights? I think there's a lot of factors that really go into that. And part of the factors that go into that is, one, the amount of insulation that's being installed and where it's at. Is it insulation at the roof level or at the ceiling level? And how much of insulation is it? Is that insulation air permeable or non-air permeable, right? The other thing is, if you're doing insulation entirely above deck, then you have that insulation. And it also has to do not even with the R value amount, it also has to do with how it was installed. I don't know if you're all aware, but manufacturers actually require that the insulation be installed to a grade 1, meaning that's how they design for that insulation to be installed. A lot of times out in the field, that may not be what happens. And part of that is because that some of that information is not translated, throughout the project. Some of that is it's just an educational thing, just providing that guidance to make sure that we get that installation. So that does have an impact. I don't know if there's enough data for me to be able to give you a really solid answer, because it's kind of an apples and oranges, and sometimes an apple maybe with a crab apple, or an apple and a pineapple type of deal. I know that designers may not be truly happy with skylights. I know a lot of times I hear, well, skylights leak. Sure, skylights can leak, but in the same sense, so do penetrations if you don't install them properly. So skylights would need to also be installed properly, and making sure that we don't have that leakage situation. So if overhang is sloped, at what point is V determined? It's the distance. So the V would probably be at that lowest point, right? That's probably typically what you would measure to. I don't know if the degree of the slope was ever so slight, because chances are you're going to have a slope, because we want things to move off the roof, right? I don't know that I would personally have an issue with it being measured to the highest point if what we're talking about is a difference of, this from here to here, because this particular building, it's a sloped building. That's, a little bit of a shed, but I would measure it here and not so much over here, just because I think it's probably easier to measure it as close to that window than as out. Is the projection factor usually or used regardless of the elevation it is placed? The projection factor is going to have a big impact, because those windows in the 2018 which I put the wrong table up, it is based off of what direction the windows are facing. So then, yes, the windows are going to have an impact as far as how you're going to look at those, and what direction they're facing. So no matter what direction they're facing, you will have to incorporate that into the design for your solar heat gain. Your solar heat gain coefficient. Sorry, don't look at this. You'll get sick. I'm just trying to get it to the solar heat gain coefficient so you can see what that actually entails. But it does have an impact on it. And you do have to provide the solar heat gain coefficient for every direction that it goes in. And as you see here, you've got southeast west in one direction, and then north that has a different solar heat gain coefficient. It actually has a higher solar heat gain coefficient because of, it's facing north, it's not really getting the sun. So the idea of the solar heat gain coefficient is how much sun is being reflected back out and not allowing that heat and radiation into the building itself. That's what the solar heat gain coefficient is. So no matter what direction it is or the elevation is, you have to utilize a projection factor. Now, your projection factor for your first floor is going to be different than what your projection factor for the bottom floor is. So a lot of times what I see, especially when we're talking about those multiple story buildings, is whatever is the most restrictive energy or solar heat gain coefficient is the one that they'll utilize. So if we looked at all of them, and ultimately we look in climate zone 3, it's a west facing window. It has a projection factor of 0.2 as the worst. It's a 0.25. But then as you move up, the projection factor then gets a little bit better. And so then you might fall under that the next story could be a 0.3, and then maybe the next story could be a 0.4. And so what do you do? Do you have different solar heat gains for all of the floors? Typically what I see is they say, nope, we're not playing that game. What we're going to do is the most energy efficient and the most restrictive requirement is the 0.25. So they'll use that 0.25 within the design of it. And it makes life easier. It may not be the most cost effective sometimes, but in a long run, it actually kind of is, because their mechanical equipment might be able to be smaller because of that particular design. Because in some areas, you're just meeting the code. And then in some areas, depending on, which floor you're on, you're going above. Okay, I now have a calculator and ready for more math. All right, perfect. We will probably have more math. I told you, I'm not very good about just letting y'all just sit there and let me talk. We're going to have a conversation. We're going to do lots of fun and exciting things. All right, so let's get back to this. The other thing that as an architect that really needs to be submitted at plan review, right? You're submitting for the permit, is we got to make sure that we have those NFRC certificates. But you don't get those NFRC certificates until you make the order for the windows. There is no way you're going to order those windows until the plans have been approved, because how many times have you had to adjust a window because you needed an egress window in another location, or that window, that operable window is too close to an exhaust. So then that operable window is now a fixed window. There's so many things that come into play. So the best thing you can do, and what I tell plans examiners all the time, is provide the compliance certificate from that framing manufacturer, because you know where you're going to order those windows from. You just don't want to put the money down and order those windows, which nobody does. And I wouldn't expect you to, but you can get that framing manufacturer certificate, and it works just fine. And they have it dialed down to the point of where we'll have that information and we can say, okay, it now demonstrates compliance with that. For inspection, they can get the actual NFRC certificate. So if we looked at this commercial energy report, right, or the framing manufacturer certificate, this is pretty typical, and this is one, I'm not going to say from which framing manufacturer for glazing it is, but if we look at it closer, our glass U factor, if we go back and we were to look what our U factor is for climate zone, what do we want to say for a U factor for fixed operable in climate zone 4? It's a 0.38. So we need to get to a 0.38. So for 0.38, we aren't going to look at this first column. This first column here is our glass U factor, and it is, if we look at number 3, it's telling us it's our center of glass value. So then we take this and we have to look at the second column, which is our overall U factor column. And if we come down to the overall U factor column to get to that 0.38, our center of glass would need to be a 0.20. So if we said our overall U factor is going to be a 0.38, then we know the glass is, the center of glass is only going to be, a part of it is a 0.20 for it. So this particular information is incredibly important and will move you along in the whole plan review process quicker without any questions. Because remember, there's a lot of jurisdictions and a lot of states and everything that's moving along that's really working on that energy compliance component. So anytime that you can help that plans examiner out and help that contractor out and help that inspector out to get exactly what it is that you designed, that's in your best interest, right? So just install that. The other thing I have is put it in your window schedule. Make it very easy. You will put in your window schedule, things like, whether it's tempered glazing, if it's fire protected, now I can't think of the word I want to say, fire glazing, right? You'll have that information in there. But go ahead and put it on here. You know that you're designing, you want all of them to be this or this. Right? It's going to be a U factor of a 0.38 or a U factor of a 0.37, depending on what it is. put that in there. Put it within the window schedule. Oh, here's a question. Should the NFRC certificate be included for the GC to provide for the glass performance that is to be installed? Now, the actual NFRC certificate comes from the glazing industry. Whoever is manufacturing that particular type of fenestration, it has to provide an NFRC certificate with it. What should be provided so that the GC has it would be that information like what I showed you here, which is the framing manufacturer's certificate, or it's a compliance certificate. And this would be the type of information I think would be very helpful for that GC. It's what's needed for the plan reviewer to say, yes, it meets code, but it's also, I think, helpful for the GC down the road. Anything that you can provide the GC that's actually tangible and not placed in that spec book, because that spec book, the spec book absolutely has a place and time to be utilized. Don't say that at all. I totally agree with it, but there are some things that get kind of hidden in the spec book. And probably now when we start talking about energy efficiency and complying with it, they're going to need to be more front and center and not necessarily in the spec book. So place some information in the window schedule. You place a lot of other things. Sometimes I'll hear, see that it's going to be low E, and that's great. You're going to utilize low E. Low E does not tell me a U factor and does not give me that solar heat gain coefficient requirement that I need. So now that we talked about insulation and windows designs, we're going to talk about something that is probably the least provided information and is going to be the most important type of information that is going to be needed. And that's dealing with our air barrier section, our air leakage section, our C402.5. So one of the things you have to determine, are you going prescriptive or are you going to do the testing? Now we're going to kind of walk through this section. And in this section, it gives you two options. You can go with the quote unquote prescriptive approach, which is you're going to follow C402.5.1 all the way through C402.5.8, or you're going to do the quote unquote performance or testing approach to it, meaning that you're going to take the building and do basically a giant blower door test to it. Now, with the blower door test option or the testing option, you still have to comply with certain sections of the code, no matter which option you utilize. So my question for you is, how many of you have utilized the testing option in your designs? Okay, wonderful. When you're doing the testing option designs, you have to be incredibly mindful as to the details that you provide, because the worst thing that can happen is you do the testing option and then you fail the test. Yes, testing option. And the reason for that is because if you do the testing option and perhaps you fail, they're not necessarily going to go back to the contractor. They're going to take a look at you and say, how come we didn't pass the test, right? And when it's after the fact, there's always that, that's craziness. What are we going to do so that we can pass this and move on? So this is where being very, very mindful what you put on the plans, I think, is incredibly helpful. So we're just going to take a look at this as if we are going with the prescriptive path. Because I think if we talk about the prescriptive path and the requirements there, it also kind of translates and bleeds into the testing option, because you have to be mindful of a lot of these things to be able to pass that test. So the next thing we have to think about is, are we going to utilize the materials or the assembly, or are we using both options? Because you can. So if you're going to utilize the material option, we have to have materials that are 0.004 CFM per square foot, that are 0.004 CFM per square foot or less. Now, the really nice thing is the code does have 16 items that already comply, and we'll talk about that in just a moment. This approach is used when prescriptive does not pass, but is close. Well, the prescriptive path, there's no testing that's involved with it. If you go prescriptive, you don't have to do the test. If you choose to go with the testing option, that's when you would have to do a few other things. Aren't air infiltration requirements only presently required in the state of Washington and exempted everywhere else? No. You have the option of doing either or in most locations. Yes, the state of Washington does require testing. A lot of other locations, once you move to out of the 2018 and you're in the 21 or the 2024, basically just about every project will be required to do the air leakage testing. So that's why getting it down now is so incredibly important, because you're setting yourself up to succeed when the other locations do have their adoptions. And a lot of locations, quite honestly, when they adopted the 2018, they also made it mandatory that you had to do the air infiltration testing, just like the state of Washington. So there are other areas, not just Washington, that does require it. So there are 16 materials that are already deemed to comply. And if you were to utilize the assembly, there are 3 items that are already deemed to comply. Those 3 items are listed here on the screen. Now, for an assembly approach, they have to demonstrate that they have an air leakage rate as the assembly that's no greater than 0.04 CFM per square foot. The material itself is 0.004, and the assembly is 0.04. Now, as you can see, those are the 3 that are already deemed to comply as an assembly, and you don't have to have the air infiltration documentation for it. Now, as far as the materials, I want to go over those materials. You have the OSB or the plywood, as long as it's 3/8 of an inch, it can be a material that can be utilized. The extruded polystyrene board can be an air barrier, as long as it's a 1/2 inch thick, or the foil-backed polyiso, 1/2 inch thick again. Closed cell spray foam can be utilized as an air barrier as long as it's 1.5 inches thick. It doesn't have to be continuous. It can be placed within the cavity as long as it's that 1.5 inch thickness. Open cell can also be, but the problem is you have to think about real estate. To meet the requirement to be an air barrier for closed cell spray foam, it's 4.5 inches thick. Now, to meet the requirement for the R value within the wall cavity, you may have to get like an R20. And if you're in a 2x4 wall, obviously, not only will it not meet the R value, it also won't meet the requirement as an air barrier. So it does matter. Size does matter in this instance, and the material and the type of material is going to matter in this particular instance. Your gyp boards and your cement boards, as long as they're a 1/2 inch thick, and it can be on the interior or the exterior. And then we have roofing membranes that are required or are permitted to be utilized. Quite possibly, hold on just a moment, Ryan. The roofing material also that's listed here can apply. We have to remember that when we talk about air barriers need to be in like the Siamese twin of insulation, because the insulation gets its R value, but all those stagnant pockets of air, when you have air that moves through those stagnant pockets of air, you strip it of its R value. And so then it's not performing the way it's supposed to be performing, and it's just basically a giant filter for the building. Roof air barriers are also required because it needs to be continuous, right? Our thermal envelope is not just insulation. Our thermal envelope is also air barriers. And so this are the types of roofing material that is permitted to be utilized. Now we've got some plaster that can be utilized, cast in place pre-cast concrete. is one fully grouted concrete block masonry. And then our steel sheets of steel or aluminum. That's how you get an air barrier for those metal buildings. Not the metal stud, but the actual metal buildings. That's how they comply with that air barrier requirement. And the solid or hollow masonry constructed of clay or shale masonry units. So stucco could potentially be one of those materials that can meet the requirement, because we do have right here, it's considered an assembly as long as the stucco or plaster is not less than a 1/2 inch thick, then it can be considered as the air barrier. Now you're like, wow, Hope, you're going to make me sick. So now my question for you is, what type of materials are often called out, but are not necessarily listed within that section? So those items that are not listed in this section would be, a lot of times I'll see that Tyvek being called out as an air barrier that's going to be utilized. Now, it could potentially be an air barrier, but we have to remember that the intent of that water-resistant barrier, the Tyvek, was as a water-resistant barrier. It's a bulk plane to allow the drainage of water, if it gets back behind that exterior cladding, the opportunity to drain out and not enter the wall assembly itself. Insulated metal panels potentially could be. They would just have to meet that requirement of whether or not they meet that air permeability. So yes, some insulated metal panels could potentially do it if they meet that requirement. They're not already in the deemed to comply necessarily component of those 16 items. So Tyvek can be utilized as an air barrier if it was tested as to be utilized as an air barrier and meets the requirements, just like the insulated metal panels, of that 0.004 CFM per square foot concept. So it does have that on here. It tells us that, hey, it can also be an air barrier, because here's the section that calls that out. But the thing is, it has to be installed in the fashion that it was tested to meet that air barrier requirement. So my suggestion in all of this for you is you can utilize it. I love using one material to take care of multiple requirements for the code, but the problem is a lot of times it'll say maybe you're going to use that air barrier. One, say it's call out air barrier, and then say it's a water resistive barrier, and they can be one and the same, that's fine, but say air barrier and water resistive barrier and say what it's going to be. Because the other thing is you really need to provide the installation instructions as to if it's going to be an air barrier also, because they're installed differently. You know, just as an example, not necessarily this one, but if it's going to be installed as a water resistant barrier, it only has to overlap 3 inches. If that particular building wrap is going to be installed as an air barrier, because it was also tested to be an air barrier, instead of overlapping 3 inches, it has to overlap 18 inches at all the joints and seams. That's a big difference. And then sometimes there's a very particular type of sealing that has to happen at the joints and seams. So that information is very pertinent if you're trying to utilize that material as an air barrier. Because if later on they decide that, you know, it's the testing concept, it may not pass because it wasn't a true air barrier that was installed. Another one is what do we utilize on the exterior a lot of times when we're talking about that fire resistant rated construction? A lot of times we're utilizing stuff or item materials such as Den's glass. Now, Den's glass, if we look here, gives us, you know, like, it's not a continuous insulation, mind you. Look at the R value. It's a 0.56 R value for 1/2 inch. that's going to have to be some really thick dense glass, right, to be able to meet that continuous insulation item. So keep that in mind. It's not there necessarily for that continuous insulation item. It's there because it's non-combustible, and it's there for the fire-resistant rated construction, because we know that it also does meet the requirement as an air barrier. And how it meets that air barrier is because it has to be tested in accordance with ASTM E2178 and meet the air permeability that it does not exceed the 0.004 CFM per square foot. If we look down here, I don't see that test going on here. But if we continue on, it says, hey, it also meets the requirement as an air restrictive barrier. How does it meet the air barrier requirement? Well, that's a really good question. I'm saying, I love that you're asking these questions. And the reason it meets that air barrier requirement is because it does meet number 7 of the already deemed to comply. As long as it's at least a 1/2 inch gyp board. Remember that gyp board can be installed on the exterior or the interior. And just because it's a fiberglass mat, you know, applied to that gyp board, it does meet the requirement as being an air barrier. It has to have all the joints and seams sealed, and that's incredibly important to know. So when we talk about air barriers have to be continuous all throughout the thermal envelope. Now, it can be located on the interior, it can be located on the exterior, it can even be a combination of the two, but it does have to be continuous. And you do have to think about it as far as what makes sense. If you decide to put it on the interior, you know, is that going to work? Now, the other thing is, I just want to bring up right here, make sure that you use the right terminology, because it's listed here as non-permeable air and vapor barrier. My first thought is, I think they're trying to say it's an air and water resistive barrier and not a vapor retarder, because those 3 terms get interchanged so much, and they have 3 very distinct requirements. So make sure you're using the correct terminology. The other thing is, think about where you're going to place that particular air barrier. In this building, they chose to utilize that foil-faced polyiso, and they chose to put it on the interior. There is absolutely nothing wrong with putting it on that interior side. The only thing is, look at all of this bracing that's going in. That's an awful lot of work to try to figure out, how am I going to maintain the integrity of that thermal envelope, right? Does liquid apply waterproofing count as an air barrier? That's an excellent question. And the answer is yes and no. Again, it is not an already deemed to comply material where it's already meets that requirement. That liquid apply liquid apply weather resistant barrier that you're talking about, some of them can be both, some of them are not tested to be an air barrier. And then again, it has to be applied in the way that it was tested to meet the requirement as an air barrier. So it's not a yes or no situation. It's, you would have to look at the very specific material to see if it can be as an air barrier. Great questions. I love these questions, everyone. So here's one where we see they did a great job, sealed all the joints and seams, you know, because that is one of the things that you have to do. Not only does it have to be continuous, you also have to make sure that you're sealing up all those joints and seams. And when you're sealing up all those joints and seams, you have to make sure that you provide that information out there in a very well concise manner, because in this particular instance, which one is our air barrier? Is it the OSB? Because the OSB is permitted to be an air barrier. Is it the Tyvek? The Tyvek could potentially be an air barrier, but as you can see, none of them have been sealed properly to be considered as an air barrier. So we have to know these things, and we have to get it documented on the plans. In this particular instance, they did a great job. They outlined it, and then they also gave us what the material was going to be. This one, not only they sealed all the joints and seams, The other thing is, sorry, I'm running a little quickly here, because I know we're on a time crunch. The biggest one I think is penetrations. Penetrations are going to make or break. And if you don't provide that information, typically you're going to find where it's going to get missed. CMU walls are not exempt from having their penetration sealed. They do have to have sealant, so provide that information. Also, don't forget, penetrations go up through the roof. Make sure that those penetrations are addressed also. Concealed sprinklers are required to have air sealing to them. The thing is, you have to reach out to the manufacturer and ask them how it needs to be sealed per their manufacturer's installation instructions. The recessed lighting has to have a gasket around it if it's part of the thermal envelope. Now, here's when I asked the question about where's the air barrier, because technically we got 4 materials right there that could potentially be the air barrier. Make it very specific. And then, of course, make sure the material you're going to use is appropriate. Because look at what happens when you don't utilize or call out a very specific material. I could look all the way through and see the interior of that particular building. Remember, fenestration also has to accommodate for air leakage. These numbers haven't changed in a long time. I see it a lot of times placed in the spec book. I have no problem with it being placed in the spec book because it's quite often a good location for it. Remember, if you have doors that access into a stairwell, elevator shaft, something along those lines, those doors have to have weather stripping unless it's part of a rated assembly. Air intakes and exhaust openings also have to have a damper. This usually is addressed on the mechanical side, but it also talks about it on the thermal envelope component, which is good because we want to make sure that there's that connection, because here you go through and make sure everything's all sealed up, and then we have this big giant opening to allow air in, right? Loading docks, we need to make sure that they have the weather stripping on there. It's in there, but I typically see it all the time. It's usually addressed. Vestibules, you got to have a vestibule. At every building entrance, there should be a vestibule. Now, you may have doors. Those doors could be employee doors. Those are exempt. It could be doors because you have to have so many doors for your egress to make sure that you have exiting going on. Those doors are not required to have vestibules. It's your building entrance doors. You may have more than one, but those are the areas that you would have it. Now, keep in mind, there's a bunch of exceptions for that. There's 7 of them, actually. Here's some examples of vestibules. Here's an example of a homemade fan that's included with it. Keep in mind, too, when you call it out, isn't vestibules only required for areas over 3,000 square feet? Yes, if it's in communication with 3,000 square feet, it would have to have a vestibule. Sorry, I'm running through this so quickly because I know we have 1 minute left. It was great. You guys had questions, and so that's the best thing. Yes, it should be if it's 3,000 square feet or more. Here's an example to keep an eye on. What is your air barrier? If it's the water resistant barrier, or if it's that, you know. Here's some, what do you think? Keep in mind, I want you to know that all your windows, if they're over 24 square feet, they constitute daylight zones. So all of a sudden, if you have daylight zones, controls may be required for it. And so that can affect things. Here's some more of things to help you help me. List what you're going to do for your air barriers. Tell them what they are. Here's a question. Understanding the penetration infiltration requirements. What are the thermal requirements for a type 1A slab over parking garage tenant improvement? Condition space of the tenant improvement also has adjacent to parking structure exhaust shaft. So when we talk about existing buildings and you're doing an improvement on it, you actually have to follow all of the requirements that are in Chapter 5. Chapter 5 is going to spell out to you exactly what it is, what you have to comply with, what you don't have to comply with. But whenever you do have a penetration, realize that you're going to have to seal it, whether it's an existing building or a not existing building, because you cannot make the building any worse than what it was prior to whatever the improvement was. So here are some help me's. I know we're at a little over time. This is me. Reach out to me, please, anytime. I'm always happy to answer questions. And you guys were absolutely great. I loved that you guys interacted. Those are the best. So thank you.